Hi, everyone. Thanks for joining. Once again, this is another one of the time-shifted IGS Global Seminar Series seminars. Um, this week, we unfortunately one of our speakers had double booked and got a little confused about the scheduling of today, so they are unable to make it. So we only have one presentation today, which is kind of nice. It'll allow him to take his time and spend some more time explaining us his interesting research. So this week we have Dr. Yefan Wang, who is a postdoc at Hokkaido University, and he is going to talk to us today about supraglacial lake evolution in northwest Greenland. As per usual, we'll save questions until the end. You can drop them into the chat or just wait until the end, and then I'll run the questions through at the end. And yeah, without further ado, I will pass it over to you, Yifan.
Okay, so can I start?
Yeah, absolutely.
Okay, I'll start to share my screen. Is it okay?
Yeah, it looks good. And if you hit presentation mode,
Yeah, it's okay.
there we go. Perfect.
Okay, so I will start my talking. Okay, so my name is Yefan Wang from Institute of Low Temperature Science, Hokkaido University. And today I will talk about the superglacial lake evolutions on Tracy and Heilprin Glaciers in northwestern Greenland. And this is from our papers just published in Remote Sensing of Environments this year. And this work was finished by me and my advisor, Professor Chien Hwa. And this work was funded by the Japan Arctic Challenge for Sustainability, the phase 2 project. Yeah, special thanks for this project. It gave me many chances to join some meetings and to go to the field work. Yeah. So the first is a short introduction about the superglacial lakes. In the summer, when we fly through the high Arctic, for example, for the Greenland or Alaska, sometimes we will see some blue patches on the surface of the ice sheet, just like these photos. So they are superglacial lakes. Yeah, these superglacial lakes will form annually when the meltwater accumulated in the topographic depressions on the surface of glaciers, ice sheets, and ice shelves. So according to some previous research, they said that the superglacial lake is darker than the ice, so we know that it will observe more energies, so it will increase the surface melt rates due to their lower albedo than the surrounding bare ice, and and also these lakes are on the surface of the glaciers, so sometimes they will drain. And it will cause the transient accelerations in ice velocity by this rapid drainage. For example, for this research, we can see that just in 2 hours, this lake disappears. And the GPS in the nearby places recorded these accelerations of this ice speed. So it seems that this superglacial lakes is important for this ice. Yeah. So because they are very important, so how we observe these superglacial lakes, we know that many of the superglacial lakes just located on very remote places. So it's very difficult for us to go to the field work. And this figure shows the superglacial lake related studies in Antarctic from a review. And we can see that, yeah, remote sensing is very widely applied method to observe these superglacial lakes. And we can see in the recent years, this related work are increasing, and we use many kinds of satellite data to monitor these superglacial lakes. And here, this paper shows the most applied remote sensing imaginaries. So not only the optical image data, for example, the Landsat series and Sentinel, but also the SAR data are also used to monitor the superglacial lakes, as well as aerial photographs. So we can see we have many data to monitor these superglacial lakes. So when we have these data, how we mapping these superglacial lakes? And one most widely method is threshold-based classifications. So in these methods, we often use some spectral index. For example, this NDWIs, which is normalize differences between the blue band and the red band, and they turn these images into this NDWI index and just to set a certain threshold to extract these lakes. And after that, to get more accurate results, researchers use a multi-threshold approach. In other words, they consider more data bands and to extract these lakes. And with the development of the computer science, the machine learning methods are also taken into the research of mapping superglacial lakes. For example, use the CART or SVM and random forest and many other machine learning methods to do it. And recently, the more advanced and complicated deep learning methods are also used to mapping these superglacial lakes. For example, this UNet CNN method is usually used into this kind of works. So back into my research, we know that these superglacial lakes will enhance the surface melting, also regulate the ice speeds. So it's very important for the surface mass balance and ice dynamics. So my research objective is to first develop an automatic method to mapping these lakes, and the second, investigate the seasonal and interannual lake evolutions on the Tracy and Heilprin Glaciers. And why I choose these glaciers, I will talk it later. And also, I will also explore the potential glaciological and climatic controls on this lake formation and distribution, also the possible effect on the glaciers. Yeah. So here I will introduce a research target, the Heilprin and the Tracy glaciers. And so where is these two glaciers? We can see this is Greenland, this is northwestern Greenland. And if we zoom it in, this is Inglefield broadening, and this is two glaciers. So why choose these glaciers? Actually, as I just say, this is a part of the Japan Arctic Challenge for Sustainability project. We do a lot of field work in these kind of regions. For example, this glaciology field work or some ocean field works, and we also have many results on it. And these two glaciers are the largest two glaciers in these regions. Actually, it is the principal source of the fresh water discharge in this field, because there are some villages and hundreds of people lived there. So in some kinds, the two glaciers are important to the local peoples. So I choose these two glaciers. Another one interesting reason is that these two glaciers exhibit different behaviors despite they are in the adjacent systems. We can see these tables. These two glaciers are comparable in the size and the frontal wise, but we can see for the frontal displacement, ice speed, and elevation changes, the Tracy Glacier is more active and it is more dynamic. So these two glaciers looks very different. So I think if we look at the superglacial lakes there, it is maybe one interesting work to do. Yeah, so I choose these two glaciers. So next I will introduce the data and methods. First is the satellite image acquisitions. By the virtue of the Google Earth engines, we have a more easy access to choose these data. So on this platform, I use the Sentinel-2 and Landsat-8 data and set some conditions for the time from 2015 to the 2021, and also this glacier mask and the cloud conditions, also the sand elevations. Anyway, I join this condition together and filter this data, and finally I get 317 Sentinel-2 data and 166 Landsat-8 data. Yeah, after this data is ready, I will start my lake detections. So I use the machine learning supervised classification methods. The first from these many data images, I selected the training scenes, and in these images, I will find the lake, where is the lakes, where is no lakes. So I draw these training polygons and extract the pixel values within these training polygons. Then I will put these values into these Google Earth Engine platforms, and they have their onboard algorithms, the random forest, and training these models. And finally, I classify these images into water and non-water pixels. And here is one result of my work. And here is the true color images, and here is the lake. And based on this result, it looks good. So I assume that I can use this result, but only eye check is not enough. So I do the accuracy assessment, and the overall accuracy is over 96% for both of the data sets. It looks good. So I will start my process. And before I get the result, I will combine these two data sets together into a dual satellite lake area time series. So does this two data set mapping the lake the same? So with these questions, I calculate the lake areas measured by the two data sets, and to see if the same lake have the same area measured by these two data sets. And it showed a good agreement. So I will fuse these two data sets together, and preferentially using the Sentinel-2 derived lake area, because it have a more high resolutions for this raw data. Yeah. So from here, I will start my result and discussion part. And the left figure is the maximum lake extent in this 8 observation years. And this color shows the water occurrence frequency, which means that in these 8 years, how many times these lakes appeared. Yeah. And from this map, we know that the maximum lake extent on the Heilprin Glaciers is 3 times larger than that on the Tracy Glaciers. We can see that the basin areas are comparable, but the lake area for the Heilprin Glaciers is very larger than Tracy Glaciers. And also, we can see the lake areas are unevenly distributed around the glaciers. And from table, we can see that the lake area increased with the elevations. Also, the lake reoccurred differently in different parts of the glaciers. For example, in the middle part of the glaciers, we can see the lakes are more tend to reoccur every year, but on the end of the glaciers or the high elevation areas, the lake seems not appeared every year. Yeah. So where these lakes tend to develop. Why the lakes like to develop here but not there? So I combine the data set of the ice speed and the mean surface slope to discuss about it. And also I calculate the surface depressions from the Arctic DM, and it is this kind of the polygons. We can see most of the lakes are developed within the surface depressions. And also these lakes prefer to develop on the low speed and the gentle slope areas, because we can see these ice speeds are decreased with the glacier on the inland directions, also as well as the mean surface slope. Yeah. Also, for these two glaciers, we can see that the Heilprin glaciers have a more slow ice speed and gentle surface slope and larger surface depressions. So I think this is one reasons why the lakes are developed more on the Heilprin glaciers. Yeah. And next, I will turn to the seasonal lake evolutions. And this figure shows the lake area and the temperatures on the Kanak stations. The pink means the total lake areas for these two glaciers, and the black line is the temperature. And we can see that the lake started developed around the mid-June and demising gradually on the late August. Also, if we look at the lake area and the temperature together, we can see the seasonal lake area change have some connection with the temperature. And when the temperature increase and the lake area increase, but it mainly in the formation stage. For example, for the 2017, 18, and 21, actually it changes with the temperature nearly for all the melting seasons. But for the 2016, 2019, and 2020, it's a different story. And before the peak of the lake area, it's increased with the temperature. But after that, it's just a decrease. No much connection with the temperature variations. So why it happens? And yeah, we calculate the lake areas in different elevation bands. For example, this 2019 and 2020s, we can see there is a huge decrease and at the middle of the melting seasons. So what happens? We check these satellite images, we can see that there is faster drainage events happens for these years. So I think for these reasons, the Moulin under these superficial lakes open, so the waters just go into the in-glacial environmentals. So the waters can't be stored on the lake. So even maybe the temperature increase, there are more melt water accumulated there, but they can't store. So that can be explained why these lake areas note varied with these temperatures. Yeah. And also, we investigate the seasonal lake variations with the runoff and melt combined with the Lachman model, the output. We can see, yeah, this I take the data for 2018, 2019, and these 4 years data for examples. We can see that the lake developed from low elevation to the high elevation regions, and this is the lake areas. We can see on the high elevation, it started late. And initial formation of the lake under the 800 meters, sometimes correlated with initial day of the runoff. We can see this red polygon is a runoff. Yes, when the runoff starts, this lake start to be observed. But on the high elevation regions, it's not. It correlates more with the day of the snow melt. We can see This purple patches is melt, and it starts with the melt in the high elevation regions. So why it is happens? I calculated the correlation coefficient between the initial day of the runoff and the lake formation, and between the day of the melt and the initial day of the lake formation. Yeah, that's the same result. In the lower and mid regions, the initial day of the lake formation correlated more with the runoff, but on the high elevation regions, it correlated with the snow melt. So why it happens? I noticed about the ice and the snow bright lakes. For example, at the end of the melt season, the high elevation regions, we can see some lakes are gradually covered by this ice and the snow. But actually, I think because these lakes are very large and deep, these lakes are not totally frozen. They are just covered by the ice and the snow. But in the next melting season starts, when this ice and the snow just melt, these ice-covered lakes just appeared, so we can observe by the satellite. But on the lower elevation regions, it will have a process of the melting and the runoff, and this water just accumulated. So I think that is one reason why on the high elevation areas, the initial day of the lake formations are correlated with the initial day of the melt, but in the middle and the low elevation areas, it just correlated more with the runoff. Yeah. And from here, I will turn to the interannual lake area variations. This is annual lake areas for these two glaciers in these 8 melt seasons at different elevation bands. And the highest lake areas for Heilprin Glaciers and Tracy Glaciers in 2019, which is very warm years. And for the lowest lake areas, Heilprin is 2015, but for Tracy is 2017. And we can see that with the low lake area years, this happens mainly on the high elevation regions. We can see that in these 2 years, these lakes on the 1,000 to 1,200 meters lakes just very low, and for Tracy Glacier just appears. And for the lakes above the 800 meters is very, very, very slow. Yeah, so I calculated the lake anomalies, normalize, and yeah, for these lakes lower than 800 meters, it is relatively stable. It is a dashed line for these two glaciers. But for these lakes above 800 meters, it shows a drastic change, especially for the Tracy glaciers. It's more drastic. It changes over 90%. Yeah, and so I calculated this lake extent with PDD for each of the glaciers above and under 800 meters. And it shows that the lake areas are more correlated with PDD above 800 meters for both of the glaciers. And for this lake area under 800 meters, there are no much, the correlation are not very significant. So why this happens? So I checked the lake extent and the surface mass balance from this LACMA model data. And here is a relative cold year, 2018. And here is a relatively warmer year, the 2019. We can see this blue patches is the lake, and this color is the annual surface mass balance. The minus is red, and the positive is blue. And we can, and I marked the 800 elevation contours here, and we can see that this lake just developed around this around the 0 surface mass balance in other words, the ELA, and it's just around the 800 contours. For example, in these years, the lakes on the negative surface mass balance regions just scarce, but in the 2019, we can see they are widely developed on the higher elevations. So we think the annual surface mass balance control the upper limit of the lake development. When it's getting warmer, the lake are more developed on the higher elevations. But even in the cold years, the lake can develop up to the 800 meters because it is maybe the lower limit of the ERA for these two glaciers. Yeah. So finally, this is the short summary of my research. The first is, the Google's engine based on machine learning methods works well on this superglacial lake classification. And this total area of superglacial lakes in Heilprin Glaciers is threefold larger than that of Tracy glaciers, which may be attributed to the topographic and the glaciology factors. And the seasonal evolution of superglacial lakes are controlled by surface, runoff, and melt, and the timing of the lake drainage. And the interannual lake variations mainly attribute to the lake development above 800 meters, which is controlled by the annual surface mass balance. So if you are interested into my research, you can just scan this QR code to my papers. And actually our group have many researchers, not just in Greenland, but also on the Antarctic, Greenland, and Patagonia. And if you are interested in it, you can just scan this QR code to our group's pages and I believe you will find more interesting things. Yeah, that's all. Thank you.
Great. Thanks very much, Yefan. That was excellent. I'll open it up to any questions. And maybe while people chat, as a non-glaciologist, what is PDD?
It's PDD. PDD, I think it's a positive degree
Positive
days.
degree.
It's just calculated from the temperature, and it's a day above the 0 degree Celsius and just a plus.
Okay, I'm more familiar with melting degree days, so I was trying to think of what the P was, but okay, positive, of course.
Yeah.
Any questions? Anyone else? Yes, Roland.
Hi.
Hi.
Very interesting talk. I have two related questions sparked by your discussion of the high elevation versus lower elevation lakes. You suggested that the higher elevation lakes might be ice-covered lakes.
Yes.
And the implication was that perhaps the lower elevation lakes might have been empty lakes which got filled by runoff.
Yeah.
So my first question is, have you contemplated whether one could get some information about those high elevation lakes from SAR data? I understand that SAR can be used to see if a lake is frozen solid or not.
Yes, thank you for your question. Yeah, that's very interesting. Yeah, I checked. I know that, and I read some papers that these SAR data can be used to detect this ice or snow buried lakes. But unfortunately, in this research, I didn't cover it. But I I have checked this Sentinel-1 data for these high elevation lakes because these lakes are very large, and I think there is some signals that these waters just exist in winters. But at that time, I do not have much knowledge how to calculate, how to quantify it. So I just omit it in these papers. But I think there is evidence. Yeah.
Yeah, and Roland, you said you had a second question as well?
Yeah, I was going to let other people jump in, but yes, my second question was again on this same issue as to whether you might be able to get some insight into the contrast between these two sorts of lakes by looking at them with DEMs, in particular, if you could get an actual time-stamped DEM to see if a lake is a sizable depression, which then fills, rather than an area where it simply seems that a lake gets uncovered and has been already persisting. So I just wondered whether the altimetry or DEMs might be another way of exploring this contrast.
Yes, thank you for your question. Yeah, that's very good. I just want to say that's a good, very advice. Yeah. Yeah, it's possible that we use the ISAT, for example, the ISAT2 data, and I have checked some of the. It's not very much tracks cover these regions. Just one or two, I think, cover some of the lakes. But I think I can do it. Also, as well as the Arctic DMs, and I think it's
Yeah,
possible.
I mean, if you can get an early season, if you can get a nicely timed early season DEM, then that might be useful to detect sort of empty lakes rather than full but snow-covered lakes, just from the shape of the topography. Anyway, thank you for an interesting talk.
Yeah, thank you.
Anyone else? No, I think that's it. Well, thank you very much, Yefan. That was a great talk. I really enjoyed that. Really well done. Nice and thorough. So yeah, so thank you everyone for joining. Again, this will be recorded and put on the IGS YouTube page if people would like to view it again later. Next week, we're back to the regular IGS seminar time, and we have Dominic Farr from GEUS in Greenland, or sorry, in Denmark. Sorry, I'm mispronouncing that. GEUS in Denmark, and he's going to be talking about. He was a recipient of the Graham Cogley Award, and so he'll be giving a seminar on that next week. And sorry, the title is The Response of Greenland's Tidewater Glacier Termini to Climate Change. And the next seminar in this time-shifted seminar series is going to take place on May 16th, and that will be Kei Oshima, again from Hokkaido University, talking about the global transports of heat, salt, fresh water, and materials by sea ice production and melt. And so Kei is an expert on sea ice remote sensing and related to plinias and sea ice growth and production. So I'm very much looking forward to that talk. And with that, we will end tonight's seminar. So thanks again to our speaker for a great talk, and thanks to all of you for joining, and take care, everyone.
Thank you.
Thank you very much for the organization. Thank you, Yefan, and thank you, David. Thanks.
Bye.
Bye.
Bye-bye.